We now go with two inspirational ideas of two different artificial intelligence ongoing projects. In first place, we will know more about NEASQC, Next Application of Quantum Computing. To bring us more details, it's with us Vicente Moret Bonillo from the Center for Information and Communications Technology Research from University A Coruña. Mr. Morillo.
Well, what I'm going to do is to talk about a little bit about the INEAS project, which is an important European project, which is an acronym from Next Applications of Quantum Computing. I'm Vicente Moret Bonillo. I'm a senior member of the IEEE, and we are talking about a 4-year project starting the 1st September of 2020. It is a multidisciplinary consortium made from 12 companies and research laboratories that is funded by the Horizon 2020 program under the complementary call of the Quantum Technology Flagship with 4.67 million euros. So it's a kind of important project. The basic aspect of the NEASQC project, the NEASQC applications of quantum computing, brings together academic experts and industrial end users to investigate and develop a new breed of quantum-enabled applications that can take advantage of the noise intermediate scale quantum systems in the near future. As it appears in the slide, NEASQC is a use case driven, addressing practical problems such as drug discovery, CO2 capture, smart energy management, natural language processing, breast cancer detection, probabilistic risk assessment for energy infrastructures, or hydrocarbon well optimization. Also, it's important to say that the project has the ambition to initiate an active European community around the NEASQC quantum computing by providing a common tool set that will attract new industrial users. And the project has received funding from the European Union's Horizon 2020 under grant agreement number 95/1821. What do we pretend with this project? Well, NEASQC aims at demonstrating that though the millions of qubits, that is the basic unit of information in quantum computing, that will guarantee fault-tolerant quantum computing are still far away, there are practical use cases for the NEASQC devices that will be available in the near future. So it's very important to highlight that NEASQC computing can deliver significant advantages when running certain applications, thus bringing game-changing benefits to users and particularly industrial users. Let's take a small look to the right side of the slide and notice that we are in the beginning of the NEASQC area, but within 5 years we will be out of the NEASQC area. So we are going to be fast in a short amount of time in the fault-tolerant quantum computing. That means that from the point of view of the industry, the industrial partners have to take into account that this new technology will be essential to perform better their job. But also from the academic point of view, it is important that the professors like me take into account that the students and the future professionals be aware about the language of the quantum mechanics and the quantum computing procedures. The main objectives that we are dealing with is to develop industrial use cases for NEASQC machines, to develop open source NEASQC programming libraries for industrial use cases, also building a strong community dedicated to industrial applications, and to develop benchmarks in the industrial area. These are the major points that we are pursuing. On the other hand, the NEASQC consortium has chosen a wide selection of NEASQC compatible industrial and financial use cases and will develop new quantum software techniques to solve those use cases with a practical quantum advantage. To achieve this, the project brings together an unprecedented multidisciplinary consortium of academic and industry experts in quantum computing, high-performance computing, artificial intelligence, or chemistry. And the ultimate ambition of the NEASQC is to encourage European user communities to investigate NEASQC quantum computing. For this purpose, the project consortium will define and make available a complete and common tool set that new industrial actors can use to start their own practical investigation and share the results. We are talking about chemistry. In fact, we are talking about CO2 recapture or drug discovery. We are talking about machine learning and optimization in the form of machine learning for oil prospection, hard optimization problems for energy management, financial applications, or HPC mesh segmentation. Also, a third big block of applications deal with symbolic artificial intelligence and graph algorithms in the way of quantum natural language processing, quantum probability safety assessment, or quantum rule-based systems for breast cancer detection. As you can see, there is a big interest to put real problems into the quantum area. The consortium is made by a quite important set of companies and universities like Atos, AstraZeneca, CESGA in Galicia, Electricité de France, Quantum Simulations, HSBC, ICEC, the University of Leiden, Tilde, Total, University of La Coruña, and Université de Lorraine. So that makes a perfect field to take together the industry and the academic world. As far as Galicia is concerned, which is my major interest in this meeting, is to show that Galicia has a lot to say in this field of applications. We are 4 centers of 4 entities, let's say in this way, like CESGA, which is the Center for Supercomputing in Galicia, the Department of Mathematics in the University of La Coruña, the Computer Architecture Group of the University of La Coruña, and the Quantum Computing and Artificial Intelligence Research Group of the University of La Coruña also. And we are responsible of dealing with several work packages. Just to take a look at one of the packages we are working on is the quantum computing in finance. We have to work with banking, machine learning, and a lot of stuff that has to do with money and with the preservation of money and the security. That forces us to make research and applications in pattern recognition, in neural networks, in automation, in algorithmics, in artificial intelligence, in data mining, in machine learning, and in problem solving, but from a quantum perspective. That probably will allow us to go from feature selection to portfolio management and finally to fraud detection, which is a very interesting thing in the domain we are dealing with. There is another work package which is also very important, which is the social part of the project that has to do with the breast cancer, in concrete invasive ductal carcinoma, that we share into the different areas like screening the cancer, the establishment of hypotheses, the establishment of diagnosis, the staging of the cancer, the therapy of the cancer, and the temporal evolution of the cancer. But all of these areas are under the umbrella of the quantum computing. For this, we use the technology of knowledge-based systems, including expert systems, knowledge-based artificial intelligence, knowledge-based engineering, in order to have a statistical corpora and in order to build quantum knowledge bases. There is an entire methodology that allows us to perform the thing, but I'm not going to go in deep because we have not much time to do it, but it's a difficult task to retrieve knowledge from experts and to encode it into a quantum environment. Let me tell you what Richard Feynman in his famous conference at Cornell said. He asked a question to the public and he answered himself the questions. The question was, will you understand what I'm going to tell you? And he himself said to himself, no, you are not going to be able to understand it. That is because I understand it. Nobody does. And this was said by Richard Feynman, who was a Nobel Prize in quantum mechanics. So the task is certainly difficult. And let me put you a simple example. In order to make the screening from the breast cancer, we have to have a lot of symbolic information that has to be coded into in the form of the production rules that are procedures, but in a quantum manner. And this is not an easy task. In any case, and I finish with my intervention, I have to make a reflection of thinking about the evolution of computer science that goes from conventional computers that do routine tasks faster. This is why we use cars to get around. Then appear artificial intelligence that make conventional systems, conventional computers smarter. And finally, we have quantum computing intelligent systems that make intelligent systems faster. And I think that I am out of time, and thank you very much for your invitation. Thank you very much.
Thank you very much, Mr. Bonillo. And the next project we are going to talk about is MISEL, Multispectral Intelligent Vision System with Embedded Low-Power Neural. For it, we have with us Victor Brea from the Singular Research Center on Intelligent Technologies of University of Santiago de Compostela. Welcome, Mr. Brea. Thank you very much for being with us today, whenever you want.
Okay. Thank you very much. All right, we start our presentation here. Just a moment, please. Here we are. So I guess that you see my screen now. Okay, as said, this is MISEL, Multispectral Intelligent Vision System with Embedded Low-Power Neural Computing. Okay, I'm Victor Brea from CITIUS, and I will tell you about this project for the next 10 minutes. Okay, what is MISEL? MISEL is a research and innovation action. It is a future emerging technologies project, and so as such, it is mainly research, all right? So we are not going to a TRL too high. Let's say that we can arrive at TRL 4 or so. The project goes from January 1st, 2021 until December 31st, 2024. There are 9 partners and 6 countries. VTT, which is like a technology center, research center in Finland, leads. And then we have 2, small, medium-sized companies, AMO and Cobilta from Germany, Finland. And then some research and innovation, centers and universities. This is our website, so you really want to know anything else, you can always get into that website. All right, what is our main goal here? Well, our main goal is to bring artificial intelligence, AI, to the edge. And what does edge mean? It means to not only acquire an image or a video, with a camera, let's say, but to process information with that camera next to the scenario where we are, let's say, monitoring or whatever you want to do, right? If you think, for instance, about, I don't know, maybe, a road with different posts, with different street lights or whatever, you can always place a camera there, and that camera capture images or video, and that video or images could be sent to a data center with a big infrastructure, like a big graphical processing unit, or a big, or even cloud, right? Or you can process the information next to the road, on the camera itself, telling you, hey, there is a car going faster, going above the speed limit, for instance. Or you can do the same next to an airport, and the camera can tell you, hey, there is a drone nearby. So it could trigger, a warning signal, so to speak. Or you can also place this system, the MISEL system, at the end of the project, on board of a drone or an UAV, to navigate, or, to tell a drone from a bird, whatever. All right. So this is the edge next to the scenario. So we are not sending images or video to the cloud or to a big infrastructure. Okay. So this is it. And so our goal is to come up with a low swap, size, weight, and power standalone system. Okay. Something that you can hold in your hand. I will show you later on. And that system should be capable of seeing in the visible and near infrared region, multispectral, and decision making to tell you, hey, there is a person here, and that person is not supposed to be there because this is a banned region, or there are some people, doing some kind of vandalism or littering, throwing out garbage, wherever. All right. So we have to make a decision and to give some semantics to the image or to the objects or to the actions, right? And this is done obviously through deep learning models or artificial intelligence, all right, on the incoming videos and or images. So get the idea that we have something that you can hold on your hand and that can make some processing, like structured information, like telling you, hey, there is an object here, or there is a guy moving fast, wherever. All right. And not only in the visible, but also in the infrared region. This is our goal. All right. So some applications here, but we are open to many more applications, right? Versus drone. This is a typical application, right? Or detection of anomalies. This is how it is written in the proposal, but we are open to many more, like pedestrians in a banned area, or running, vandalism, whatever. I just brought some of them here. So this is the concept. Different components, different elements in our project. So we have different processors. We design chips in essence, all right? We design integrated circuits. So we have a cellular sensor processor capable of acquiring an image, but not in a conventional RGB image, red, green, the images or the photos taken by your iPhone or by your mobile phone, but we take in events, on-off events, which is another representation of a video or of a sequence. So we design, what we call here cellular sensor processor, providing events, and then we have two more processors here, to extract information. So let's see that we have three. Let's say that we have three sensors, so three processors. So in the cellular sensor processor, we have quantum dots made out of graphene, and these quantum dots can be tuned to acquire in the visible or in the infrared region of the spectrum. Next to that, we have a chip, okay, to acquire and to process that information, and then two more processors to process information with very, emerging technologies like FRAM technology, which is a non-volatile memory capable of having the image for a long time. All right, this is more or less what we have, what we do, the components of the system. Here, I tell you, we have an image sensing and computer vision on events. This is one of the components of the project. Neural networks, which, I mean, this is artificial intelligence. This is where the artificial intelligence is, within the neural networks and within the hyperdimensional computing, which is a novel emerging computing paradigm dealing with vectors of tens of thousands of components. We have mixed mode CMOS design for processing, not only digital as computers do, but also analog as it is the real world. Okay. Another component is device manufacturing, another component of the project, with FRAM for storage and processing and quantum dots for sensing in the multispectral regime. This is what we have, the components of the project. This is just to give you an idea of what we expect to have at the end of the project. This is how the device might look like. This is a system designed here at CITIUS, part of a thesis, of a doctoral thesis, and we designed everything. Everything you see there was designed by us, okay? All the components of this system, and also a chip inside inside this green box, capable of seeing, capable of acquiring images, right? This is part of a thesis, as I told you. So our final system would look like something like this, all right? Just to give you an idea how this could be like 10 centimeters by 5 centimeters or something like that. Just to give you an idea of the area. So it is low area, low size, low power consumptions to be portable and to be next to the scenario, to the sensing scenario and everything. This is so far what we did. Actually, we've submitted 2 chips for fabrication quite recently. One of them with a cellular neural network engine here with the memory computing processing capabilities. I will not go into more details here. And a hyperdimensional computing chip. So we have submitted these 2 chips 1 week ago, and this is one of the milestones of the project within the first year. And now we are expecting them to come back to measure them in the lab. This is just to give you an idea of what we're doing. Next, and just to conclude my talk, bring these ideas. What we do is a low swap, size, weight, and power system, standalone device. Standalone means that it's able to do everything. We don't really need to send images or to send data out to a data center or to the cloud. We can do it with a smart camera. Keep this idea in mind. In the multispectral regime, bringing artificial intelligence to the edge, okay? To a camera, not to the cloud or to a big infrastructure. And we have novelties, not only in the design of the neural networks and the hyperdimensional computing and the chips, but also with devices. We implement FRAM technologies and quantum graphene dots. And just to conclude, during the first year, what we did was to design 2 proof of concept chips, and we expect to bring everything together with the rest of the partners along these 3 next years until December 31st, 2024. And that's it. Thank you very much for your attention.